we briefly explain the AI research and the applications conducted in our lab. Okay, first we briefly mention what is the niche for IE majors to study AI. It's based on two perspectives. First, the math required for to build the neural network like optimization, linear algebra, statistics, or other math studied by IE. And secondly, because IE major use these mathematical models for production and the quality management. So we understand the domain problem. So when we use the neural network to build the smart manufacturing and service, because we know how to apply it to real world problems. So that's why although EE or CS majors can also study the AI, but their focus are mainly on the algorithm or mathematics side. Okay, they are difficult to communicate with domain experts for application. And another extra benefits of our lab is because we have been using Python and Unity for a long time. And Python is the language for built-in deep neural networks. And Unity is the tool for reinforcement learning. So our lab, compared to other IE majors, are easier to enter the deep learning and the reinforcement learning. This slide shows some results of our previous research. But the point is, our research, we focus on the research that the result can be applied to real world. Okay, so we are application-oriented research. Of course, in academic, we need publications. These are the related publications, okay? And if we have a postdoctor, Jia Xuan, she is very good in writing these academic research papers. This is another research area we have been working on. As I said, it's also focused on application-oriented. Here we want to use the sensors invented by Victor to see whether the data recorded by this sensor can be used to measure the balance ability. Okay, here is the publications. And also another advantage of IE students to do AI is because if you want to do useful research, you usually need multidisciplinary cooperation, and we IE majors are easier to communicate with different domains people than the EE or CS major. So for example, if we want to build a machine learning model to determine the balance ability from the sensor data, we like to communicate by telling which features are important features. Okay, the details, we publish this result in IEEE sensor. If you are interested, you might take a look at the paper. And I will skip these 3 stages of AI, and I will talk about it later in class or in our meeting. Okay, so the first, actually the most important thing for deep learning-based AI is computer vision. Okay, so in our lab, we already implement a lot of deep neural networks for computer vision, from the classification to semantic segmentation, where we want to label or classify at pixel level. We want to classify which pixel belong to cat, which pixel belong to mountain. And also we will want to recognize what object and image you have and their locations. And finally, we want to do to understand the boundary pixel of each object is called instance segmentation. Here we show the important computer vision neural networks by year. Of course, the first is 2012 when AlexNet comes in and beat the traditional machine learning algorithms. And then comes to VGG, and then comes to ResNet, all by He Kai-ming. And in terms of the semantic segmentation, 1915 unit. And in terms of the object detection, comes 1915 faster RCNN by He Kai-ming, and 2017 the instance segmentation mask RCNN by He Kai-ming. These numbers are the Python program we implement in data visualization course. Here are some examples of faster RCNN for object detection and mask RCNN for instance segmentation. All these examples are run on the PC with 1060 GPU. Here's the examples where we use the fast RCNN to detect and track a person. And if we extend the instance segmentation, we can further label and train the neural network to identify the joint. Okay, the joint. So here we show the key point detection on body or key point on face. And in many situations, when we finish develop the neural network, we want to deploy the AI models to an edge computing device. Okay, so here we deploy our object detection model to the Jetson Nano edge computing device. Here we deploy the object detection YOLO model to the TX2, Jetson TX2 edge computing device. And in some situations, the user want to do AI on the mobile phone. In this time, since the mobile phone does not have enough computing power to calculate the key point detection, so we use the AIoT solution, like the one you learned from Professor Su's IoT class. We send the image through the internet to a server, and in the server we calculate these joints and then send the image back. So we can run this application on your mobile phone. And here's another IoT applications where we remotely control the robot to monitor something. Okay, so the computer vision let the AI has perception ability, just like the human is able to see and to hear. But only perception that does not contain the power to perform an action. So if the AI has the perception capacity, it's just like a human with eye and ear, but without hand and legs. So it can only perceive, and while it finds some problem, it can only tell the human to do something. So we need to go further to combine the computer vision with reinforcement learning to train the AI to see something and then to perform actions. So for example, like the self-driving car or intelligent robot or play the Go. The reinforcement learning is another focus point of our lab, because we already know the simulation software. And the reinforcement learning is like human. We let the AI interact with the simulation environment. We let the AI interact with the simulation environment, and to try to do trial and error and try to learn the optimal policy that will give us the maximum long-term reward. Okay, reinforcement learning, if you want to run it, you better understand is underneath math. I will discuss the math behind reinforcement learning in class. Okay, so here I just skip. And if you train the reinforcement learning, it's like you see your life. For example, if we just give intrinsic reward, okay, then you will find if your reward is not enough, your AI will, just like a human, just feel lazy and circle around, will not bother to reach the goal because it's too bothersome to why bother to spend effort to reach the long-term goal. However, if you put your penalty too much, then you will find your AI tends to give up or even to suicide by colliding the wall. So in addition to extrinsic reward, we should let AI have intrinsic motivation, just like human, like the honor, responsibility. But honor and responsibility are difficult to model. So here we follow the UC Berkeley's approach to use the curiosity to model the intrinsic motivation. I will explain these details in our VR course. Similarly, here on the left-hand side, you see we train the AI using a deeper neural network. It contains 2 layers, each layer 128 nodes. And as you can see, in this case, the AI is overfitting, so it performs very well in the training environment. Did you see the turning angle is very sharp compared to here? Okay, very good in training, but then it performs very poor in an unseen environment. It cannot generalize. On the other hand, on the right-hand side, we use a shallow neural network. It contains only 1 layer and 36 nodes. So as you can see, the performance in a training environment is not that good. As here, the turning angle is a little large, but the AI can generalize to the unseen environment. Okay, so the reinforcement learning is notorious for its difficulty to train, but the reward is also large. Once it is successful, you get an agent that can generalize to the unseen environment. In many situations, like self-driving car, it's invisible to define a reward because, for example, you can say how much penalty is enough if the car hit people. So in this case, we cannot use reinforcement learning. We have to use imitation learning to let the AI learn from people. In other cases where the task is difficult, we better let people to teach the AI, so the AI does not learn from scratch. It will speed up the learning process. So this is called imitation learning. And we are currently trying to use Scale, which apply the GAN, generative adversarial network, with the reinforcement learning. to do imitation learning. I will explain the details of this GAN based imitation learning in class. Here are some SOTA of the intelligent robot products, state of the art. But these robot products are very expensive, and we cannot customize them for our needs. So another important focus of this lab is to develop intelligent agents using our own technology. So we investigate perception, we study reinforcement learning, along with the hardwares like power, mobility, communication. Here are some preliminary results of intelligent robot. We called it 小智. 小 means smart. 智 is 原智. In Chinese, it also means smart. So here is the 小智 Smart Z developed using TurtleBot. Here is little z, small z, 小小智, okay, developed using JetBot. Okay, with this we conclude our introduction of our lab.